enthalpy of neutralization. It is really an important reaction enthalpy. In so many previous questions, you can find the problems based on standard enthalpy of neutralization. Neutralization means it is reaction between acid and base. When acid and base are reacted, when these are mixed, energy is released. So, neutralization process is exothermic. So, standard enthalpy of neutralization is always negative. These are the basic thing we have to do. Neutralization means it is reaction between acid and base. All neutralization processes are exothermic, so neutralization enthalpy is negative. Then, first I am discussing its definition with example. Standard enthalpy of neutralization means it is enthalpy change during neutralization. That means reaction between acid and base, but one equivalent acid and base. Generally, we are using 1 mole in most of the definition, but here not 1 mole, that is 1 equivalent. 1 equivalent acid and base, that is known as standard enthalpy of neutralization. I am giving here 3 examples. All are balanced equations. HCl 1 mole means 1 equivalent. NaOH 1 mole means 1 equivalent because their balances are 1. So, these are balanced equation and it is 1 mole, 1 equivalent, 1 mole, 1 equivalent. So, HCl and NaOH means 1 equivalent plus 1 equivalent. There is no doubt. In here, in balanced equation, I use half H2SO4. Why? 1 mole H2SO4 means 2 equivalent. By definition, we want 1 equivalent. So, half H2SO4, 1 equivalent, NaOH, 1 equivalent, there will be reaction. Then, HCl, 1 mole, 1 equivalent, no doubt. What about AlOH thrice? Its valence is 3. 1 mole means 3 equivalent. 1 by 3 mole means 1 equivalent. So, in this balanced equation, we have to focus the point acid and base are 1 equivalent substance. In these reactions, there is a common substance. What it is? H2O. In all reaction, 1 mole H2O is formed. So, we can define it as follows. What it is? It is the enthalpy change during the formation of 1 mole H2O. During the formation of 1 mole H2O. How? By the neutralization of acid and base. So, general definition, it is the enthalpy change during the reaction between 1 equivalent acid and base. Another definition, it is the enthalpy change during formation of 1 mole H2O liquid. 1 mole H2O liquid by the neutralization of acid and base. Okay. This neutralization process involves 2 steps. Neutralization means reaction between acid and base. It involves 2 steps. Number 1, acid and base undergo complete dissociation to ions. Complete dissociation of acid and base to ions. To react between acid and base, first it should completely dissociate into ions. Then these ions combine to form salt and water. This is salt, this is water. Based on acid and base, this salt also changes, but water is common. So, I am focusing on that water. 1 mole H2O is formed by combining H plus and OH minus. So, what is second step? Formation of 1 mole H2O liquid by combining H plus aqueous and OH minus aqueous. Neutralization process involves 2 steps. Number 1, complete dissociation of acid and base into ions. Then these ions combine to form salt and water. I am focusing on that water. 1 mole H2O liquid is formed by combining H plus and OH minus. First, I am considering neutralization of strong acid and strong base. HCl is strong acid, NaOH is strong base. Strong acid and strong base undergo complete dissociation. So, to dissociate this acid to completely, energy is not required during neutralization. Why? It is already completely dissociated. So, this enthalpy is 0. What about NaOH? NaOH is strong base. It is already completely dissociated. So, to dissociate NaOH completely, energy is not required. What about second step? It is common for all acid and base. What it is? Formation of 1 mole H2O liquid by combining H plus and OH minus. This value is fixed. That is minus 57.1 kilojoule. 1 mole H2O liquid is formed during combination of H plus aqueous and OH minus aqueous value minus 57.1 kilojoule. Listen. This value is 0, this value is 0, this value minus 57.1. According to Hess's law, enthalpy of total reaction will be minus 57.1 kilojoule. That is standard enthalpy of neutralization of strong acid and strong base. So, I am specifying the point. Neutralization enthalpy of strong acid and strong base is fixed. That value is minus 57.1 kilojoule per mole or minus 13.7 kilocalorie per mole. That is simply energy change. Kilojoule is converted to kilocalorie. This value constant. Neutralization enthalpy of strong acid and strong base is constant. That value is minus 57.1 kilojoule per mole or minus 13.7 kilocalorie per mole. If it is weak acid or weak base, just considering another example. And weak base. CH3COH is one of the weak acid. NaOH is strong base. I am considering one weak acid with a strong base. It can also be weak base. We can explain it another example. Now, one weak acid and a strong base. This is the reaction. NaOH strong base undergo complete dissociation. Energy is not required. But CH3COOH is weak acid. It undergo partial dissociation only. So, to dissociate them completely, energy is required. That energy is represented as dissociation enthalpy. What it is? Dissociation enthalpy of weak. Now, acid, base can also. Dissociation enthalpy of weak acid. Second step is common. What is second step? 1 mole H2O liquid is formed by combining H plus and OH minus. Its value is minus 57.1 kilojoule. So, neutralization enthalpy of this reaction cannot be minus 57.1. By applying Hess's law, we can say that neutralization enthalpy of weak acid or base equal to dissociation enthalpy of weak plus this value minus 57.1 kilojoule. If we are using kilocalorie, we have another value minus 13.7. This is the equation. So, when weak acid or weak base is present in the reaction, its neutralization enthalpy cannot be minus 57.1 kilojoule. Its dissociation enthalpy is also considered. That dissociation enthalpy plus minus 57.1 will be neutralization enthalpy of weak. By including dissociation enthalpy, we can say that neutralization enthalpy of weak acid or weak base will be less negative than neutralization enthalpy of strong. We have to focus that as strength of weak acid decrease, neutralization enthalpy also decrease. Similarly, as strength of weak base decrease, neutralization enthalpy also decrease. Ka means dissociation constant of weak acid. If Ka decrease, neutralization enthalpy of weak acid decrease. Kb is neutralization enthalpy, dissociation constant of weak base. If Kb decrease, neutralization enthalpy of weak base also decrease. So this is the final point. Neutralization enthalpy decrease as strength of weak acid or weak base decrease. Thank you.